Hello everybody, I'm Alessandro Granelli and I'm a PhD student in astroparticle physics at SISSA. I will talk about aspects of high-scale leptogenesis with low-energy leptonic CP violation. The work I will talk about has two motivations. Firstly, neutrino masses and mixing, and secondly, the baryon asymmetry of the universe. These two are major problems in modern physics as they don't find any solution in the standard model of particle physics and in cosmology. In the work I will talk about, we rely on the type 1 seesaw model, which is a minimal and very natural extension to the standard model, consisting of adding at least two heavy Majorana neutrinos to the standard model. So with a Majorana mass term and a Yukawa coupling to the left-handed lepton doublet and to the Higgs field. After the electroweak symmetry breaking, this piece of the Lagrangian leads to the light neutrino masses and relates the light neutrino mass matrix to the Yukawas and to the inverse of the mass matrix of the right-handed neutrinos. And this is the famous seesaw formula. However, there is the well-known fact that in this model, there are infinite possibilities to reproduce the masses of the light neutrinos. And this is encoded in the Casasibara parametrization, where the Yukawas can be written in terms of the PMNS matrix, the matrix of the light neutrino mixing, then the masses of the light neutrinos, the masses of the heavy neutrinos, and then there is an arbitrary 3×3 complex orthogonal matrix R, which can be parameterized in general by 3 complex angles if there are 3 heavy neutrinos, or by just one complex angle, with a real part that I will call X and an imaginary part that I will call Y, if the lightest neutrino is assumed to be massless, so either normal hierarchical case or inverted hierarchical case. Then the other piece of the framework is leptogenesis, that is the generation of a lepton asymmetry in the early universe thanks to the out of equilibrium lepton number violating C and CP violating decays of the right-handed neutrinos and inverse decays. The so generated lepton asymmetry is then converted into a baryon asymmetry of the universe by the standard model sphalerons happening, which are effective above the electroweak scale. I will mention many times in the next slides low energy CP violation. What I mean by this is that the Yukawa in the type 1 seesaw model is CP violating only because of the Dirac phase delta and or the Majorana phases alpha 2,1 and or alpha 3,1 of the PMNS matrix U. In other words, the R matrix in the Casasibara parametrization will mostly be considered to be CP conserving. In particular, Y can be, is set to 0, or X is set to 0 or integer number of pi. The so-called flavor effects in leptogenesis are relevant in the work that I will talk later on. Let me just briefly describe those in this slide. So we have the decays in the early universe of the right-handed neutrinos into the Higgs doublet and the left-handed lepton doublet. The lepton product of the decay is a coherent superposition of flavor states. Now, in the early universe, if it were not for the standard model Yukawa interactions, the flavors of the leptons will be indistinguishable. However, the standard model tau and muon Yukawa interactions, when they enter in equilibrium, becoming faster than the expansion of the universe, make the flavor distinguishable. And in particular, these interactions destroy the coherence of the superposition of flavor states psi. In this sense, these are called the coherence effects in leptogenesis, and they are purely quantum effects. In the early universe, one can distinguish between 3 different flavors. The first one is the single flavor regime, that happens above 10 to the 12 GeV, when the tau and muon Yukawa interactions are slower than the expansion of the universe. In this case, the flavors in the early universe are indistinguishable. And one can use the single flavor approximation in leptogenesis, neglecting from the game the tau and muon Yukawa interactions. And one can work with the classical single flavor Boltzmann equations to study the time evolution of the quantities involved and of the lepton asymmetry. There is the two-flavor regime. The two-flavor regime happens between 10 to the 9 and 10 to the 12 GeV, when the tau and Yukawa interactions are faster than the expansion of the universe, while the muons are not. So in this case, the tau flavor is distinguishable from the other two. Then one can work with the two-flavor approximation, neglecting the muon Yukawa interactions from the gain, and can work with the two-flavor Boltzmann equations if the tau and Yukawa interactions are assumed to be infinitely fast. Then there is the three-flavor regime below 10 to the 9 GeV, when both the tau and mu nuclear interactions are faster than the expansion of the universe. Then the three flavors are distinguishable, and again, one can work with the three-flavor Boltzmann equations if the tau and mu nuclear interactions are assumed to be infinitely fast. However, there are also other type of equations which always takes into account these decoherence quantum effects, and these are the density matrix equations, and they are useful because they are valid in all in the single flavor, the two flavor, and the three flavor regimes, and also in the intermediate regimes, because they always take into account these quantum decoherence effects, and also in the various limit they reproduce the Boltzmann equations. In the work that from now on I will talk about, we dealt with leptogenesis over a wide range of masses, from 10 to the 8 GeV to 10 to the 14 GeV. We worked with a hierarchical spectrum for the right neutrino mass spectrum, and we solved different sets of equations, the Boltzmann equations with one flavor, with two flavor, and with three flavor, and also the density matrix equations, and we have compared the results obtained with these different sets of equations. And we used to do so the Ulysses Python package, which can be found in the reference that I mentioned here in these slides. Now, let me just mention the general features of this work. Here are two plots that show the baryon asymmetry of the universe in modulus against the mass scale of leptogenesis, namely the mass of the lightest heavy neutrino. In this figure, it's shown the solution to the different sets of equations that we have used. So in blue is the density matrix equation. In yellow is the single flavor Boltzmann equation. In green, the two flavor Boltzmann equation. In red, the three flavor Boltzmann equation. Then we have separated in solid blue the positive baryon asymmetry predicted by the density matrix equation. In dashed blue, the negative contribution. We have assumed mostly in the entire work vanishing initial abundance of neutrinos, namely at the beginning of leptogenesis, there are no neutrinos in the universe. This is what we have called the standard behavior of the baryon asymmetry, because at 10 to the 9 GeV, there is the transition from the two flavor to the three flavor regime, and the density matrix recovers the three flavor Boltzmann equation in the three flavor regime. Then we have the two flavor regime, where the density matrix equations reproduce the two flavor Boltzmann equation. Then we have a sign change in the density matrix solution at 10 to the 12 GeV when the single to two flavor transition happen. Now, this is a peculiar thing that we have investigated and studied in detail. In particular, we have studied when this sign change happens and at which mass scale happens. Another important feature is the following. Notice that at the right, where the right plot corresponds to CP conserving R matrix, namely low energy CP violation, while the left plot corresponds to CP violating R matrix. Notice that in the right plot, there is no solution to the single flavor Boltzmann equation. This is because the single flavor Boltzmann equation, in this case of low energy CP violation, predicts zero asymmetry, because they don't take into account the quantum tau decoherence effects, while the density matrix equation, they do take these effects into account, and actually these are enough to produce, as you can see, a plateau region in the baryon asymmetry. So the baryon asymmetry, because of these tau decoherence effects at high scale, is independent on the scale. Let me show you other examples. To be more quantitative, we have decided to work with, at first, with low energy CP violation only from the Dirac phase, delta. So we set to zero the Majorana phases. We work with the normal hierarchical spectrum and real R matrix. So we put at first y, the imaginary part of the angle of the Casares matrix, to zero. Then here are two examples for different values of the real part of the angles of R. You can see that this is a non-standard behavior of eta B because of the following. So first of all, the 2 to 3 flavor transition happens with a sign change. Then the 1 to 2 flavor transition happen again with a sign change, but at a mass scale that is much less than 10 to the 12 GeV. Here in this case at the left at 10 to the 11 GeV. While at the right, it overlaps with the 2 to 3 flavor transition at below 10 to the 10 GeV. So this is far from what one would have naively expected. The 1 to 2 flavor transition happen at 10 to the 12 GeV. Indeed, in this case, it happens at so small masses that actually the density matrix equations that are correct because they take into account the quantum effects, are enhanced with respect to the two flavor Boltzmann equation solution, which actually appears to be very inaccurate, or even in the two flavor regime. Then we have investigated in detail also the regions of successful leptogenesis and in the parameter space. In particular, we have found what are the values of the ranges of values of the real angle x of the Casasi-Barra matrix, the PMNS phases, delta, and then also the Majorana phases, and the range of masses for which one can have successful leptogenesis. Namely, when the Barana symmetry predicted by the density matrix equation is positive and of the correct magnitude. Here you can see that the regions of successful leptogenesis are the ones surrounded by the solid contours. Inside, the Barana symmetry can be reproduced, while outside, in the blue regions, and the Barana symmetry in modulus is too small compared to the observed one. And inside the dotted contour, in magnitude is okay, but it has a negative sign, so it is not correct. So the only regions here, in this case, appear only when delta lies between pi and 2 pi. So the Barana symmetry is of the positive sign only if sign of delta is negative. So we found a correlation, a one-to-one correspondence between the sign of the Barana symmetry and the sign of delta. Then we also found that the minimal mass scale for leptogenesis in this case is at around 2.55 times 10 to the 11 GeV. Then we also perform the same analysis, but instead we chose the real part of the matrix R to be 0, of the angle of the matrix R to be 0, while the imaginary part different from 0. And in this case, we performed a similar analysis. We found a correlations, however, an opposite correlation, in the sense that now, in order to have a positive Barana symmetry, we need the sign of delta to be positive. And then we found a very similar minimal mass scale for viable leptogenesis. We have also performed the same analysis for the inverted hierarchical spectrum, and let me just mention that there are very similar features, but most importantly, we found that the minimal mass scale for leptogenesis is lowered by almost 1 order of magnitude, and it is at 4.6 times 10 to the 10 GeV. Then we have also performed the same analysis. In the case the low energy CP evaluation is provided only by the Majorana phases, and so here is the plot showing the regions of successful leptogenesis in this case for normal hierarchical spectrum, and we found a minimal mass scale for at 3 times 10 to the 10 GeV. And then for the inverted hierarchical spectrum, finding a very similar minimal lower bound for viable leptogenesis on the mass scale. Let me sum up the major highlights of this work. So we have studied leptogenesis for over a wide range of masses, covering all the different flavor regimes from 10 to the 8 GeV to 10 to the 14 GeV. In the hierarchical case for the right-handed heavy Majorana neutrino mass spectrum, solving the Boltzmann equations and the density matrix equations and comparing the result. We have performed a detailed analysis of the 1 to 2 and the 2 to 3 flavor transition, showing that the Barana symmetry may change its signs at this transition. We have shown that the tau decoherence quantum effects can still generate the Barana symmetry of the universe in the single flavor regime when there is a low energy CP evaluation. This is in contrast with what is predicted by the single flavor Boltzmann equations, as this predict zero asymmetry. And this is a confirmation of what was already mentioned in an earlier paper in 2018 that I mentioned, that I cite here. However, we have investigated this feature in greater detail. Then we have discovered that two-flavor Boltzmann equation actually can be very inaccurate, even in the two-flavor regime, contrary to what is naively thought to be the case. Then we have discovered the one-to-one correspondence between the sign of the Barana symmetry and the sign of delta in the case of low energy CP evaluation only from the Dirac phase delta. Then we have revisited the ranges of masses and PMNS phases for viable leptogenesis in the case that we have studied. And then let me just mention that these scenarios of leptogenesis are actually testable and falsifiable as in low energy neutrino experiments, as for example, if one is able to measure more accurately the Dirac phase delta, or to measure the Majorana phases, one can set the scale of leptogenesis in our scenarios, or at worst, one can reject completely our scenarios. With this, I conclude, and I thank you all for your attention in this talk. And let me also thank the organizers of the TAUP 2021 conference, which gave me the opportunity to talk about this project. Goodbye.